Hello class, welcome back. It's me, Professor Hunter, and today we're going to be going over chapter 3, which talks about momentum and energy. Alright, so first let's start with, what is momentum? Well, let me just give you the equation and then I'll try to describe it to you in words. So usually we use the letter P for momentum. I'm not exactly sure why. I guess because we can't use M because M is already used for mass, and yeah, so we use P for momentum, and momentum is given by the mass times the velocity. All right, and so if you're looking at the PowerPoint, it says momentum is inertia. It's inertia in motion. All right, and so I think that kind of makes sense from looking at this equation, right? Because we know mass basically tells you how much inertia something has. So the more mass, the more inertia. And then velocity just tells you that it's some mass that has some velocity or is in motion. So momentum is inertia in motion. But notice it's a little bit different from force, where force is given by mass times acceleration. So if a mass is accelerating, then it must have some force applied to it so that it can accelerate or change velocity. But if some mass, it just has some velocity, then it has some momentum. So very similar, but different concepts here. All right, so let's talk about a few examples of momentum. All right, so let's say we have a ball here, and this ball is rolling in this direction with some constant velocity. This is a constant velocity. And it has a constant velocity of, let's say, 10 meters per second. And let's say the mass of this ball is 5 kilograms. Well, then what would the momentum of this ball be? Well, it's pretty easy, right? The momentum, P, would be the mass times the velocity. And so it would be basically 5 times 10. And so for this ball has a momentum of 5 times 10, which is 50 kilogram meters per second. Yeah, I got ahead of myself. Energy is measured in joules, but momentum is measured in kilogram meters per second. So a weird unit, not something you really need to remember, but just notice that it's basically the kilograms, which comes from the mass, and then the meters per second, which come from the velocity. Okay, and so basically, if you were to increase the mass of this ball here, and let's say the mass instead of 5 is 10, but the velocity is still 10 meters per second, well then that would increase the momentum to 100, right? So basically, if you increase the mass, you increase the momentum, or if you increase the velocity, then you also increase the momentum. All right, so next, let's talk a little bit about impulse. Impulse. Well, you can kind of think of impulse as impact. These two words are kind of synonymous. Whenever you think of impulse, you can basically think of how much something is impacted. And the equation for impulse is given by, so impulse is basically equal to force times time. So the amount of force applied to something in some given time. And that's going to be also equal to, what's that going to be equal to? Well, that's going to be equal to mass times what? Times velocity. Or better yet, this is basically just the momentum, right? So the impulse is given by actually the change in momentum, where this triangle again means change, right? So the change in momentum, which is given by the force times time, is the impulse. So the impulse is force by time, and the impulse can also be thought of as the change in momentum. And so how did I basically make this jump from here to here to here? So just to kind of break it down a little bit, we know acceleration is given by the change of velocity over the change in time, right? Well, we can also write the acceleration as force divided by mass, right? From Newton's second law. And now, just using basically this part here, I can rearrange this to get basically what I have up here. So if I take this m, multiply it to the other side, and take this time and multiply it to the other side, I get basically mass times the change in velocity is equal to force, the force times the change in time. And so now we see here, we basically have what I wrote up above here. And we know basically mass times the change in velocity is basically just the change in momentum. So that's kind of how we basically get this impulse equation. So let's go through a kind of an example here. So let's say we have a cannon. So this is a cannon. All right, so this cannon basically is real long, has a cannonball in there. The cannon is going to fire. The cannonball is going to travel through this tube, right? And then shoot out of this end. So what if I were to make this cannon shorter versus how long it is now? Let's say if I made it shorter to where it looked more like this. So what would be the difference in the impulse between these two situations here? Well, basically, this larger cannon is going to have a greater impulse. It's going to have a greater impulse because it's going to spend a greater amount of time inside of here. And so since the cannon, or this cannon here, spends a greater amount of time inside of, I guess, this tube, so to say, and so it spends a greater amount of time, then it's going to have a greater impulse when it shoots out. Versus, this smaller one, it's not going to spend as long, so it's not going to have as great amount of time as this one. inside the cannon, so the impulse for this smaller one is going to be even less. Or you could think about it in terms of the change in momentum. So we know this longer cannon, since it's longer, it's going to have a greater impulse, so it's going to shoot this cannon out even faster. So if it shoots it out faster, then the change in momentum for this one's going to be greater than the change in momentum for this one. All right, and so if you're looking through the PowerPoint, they basically go over a few other examples of impulse. I think you can kind of read through those on your own. So next, I'm going to get into the conservation of momentum. So now I'm going to talk about the conservation of momentum. Let's see, conservation of momentum. And what I mean by conservation, whenever I say conservation, it means the initial is going to equal the final, basically. So if you have a situation, well, let me write out the equation first. Conservation of momentum basically means the initial momentum. So we know P is for momentum, and I got this little I for initial. The initial momentum is going to be equal to the final momentum for a given system. So if the momentum is conserved, then we can say this here. We can say the initial momentum is equal to the final momentum. And so let me give you an example. Let's say you're playing pool or billiards, and there is a pool ball here. Let's say this is the, let's say this is the, let's just say it's a ball sitting there. And you have this other ball coming with some velocity this way. All right. And let's color this one. Let's color this one red. So this ball is just sitting here at rest. It's not moving. If we have this other ball coming in, this ball hits this ball. This white ball is basically going to transfer all of its momentum to this other ball. And since there's no outside forces, no outside forces, it's just this velocity of the ball hitting that one, then all the momentum is going to be transferred over, basically meaning after this one collides with this other one, the first ball is now not going to be moving, and it's going to transfer all of this momentum to the red ball. And so now the red ball has that same velocity which the white ball hit it with. So that's kind of what I mean by momentum being conserved. Now, under what conditions is the momentum conserved? Well, it's conserved when there is no external force. So whenever there's no external forces, we can say the momentum is conserved. So now let's kind of talk about collisions, because there's two types of collisions we could talk about whenever we discuss basically conservation of momentum. Collisions. So there's two types of collisions. There is elastic collisions, and then there's inelastic collisions. So there's two types of collisions, elastic collisions and inelastic collisions. An elastic collision basically means one object hits another object and they basically bounce off of each other. So whenever you hear elastic, you can kind of think of the word bounce. So whenever you hear the word elastic, you can think of the word bounce, meaning that when one object hits another one, it's just gonna bounce away. And so kind of think of bounce when you hear elastic collision. And an inelastic collision is when two things collide and they stick together. So inelastic is basically the opposite of bounce. So for inelastic, you could think of things sticking together after they collide. So this is when things stick together. Well, for both of these cases, the momentum is conserved. And so knowing that the momentum is conserved for both of these cases, we can basically deduce a few things about the scenario. So let me give you a scenario of an elastic collision. So for an elastic collision, how do you spell that? Elastic. So let's say I have big ball here and it's going this way. This ball has a velocity of 5 meters per second and its mass is 10 kilograms. And let's say there's a smaller ball here at rest. And so the mass of that ball, let's say it's 1 kilogram. Well, let's say these two balls collide because this one has some velocity going that way. It's going to collide. What is going to be the velocity of this smaller ball after they collide? And let's say we also know that the final velocity of this ball over here is going to be 0. So now we know after they collide, now this big ball has a velocity of 0. And now the smaller ball has some velocity. And so because we know the momentum is conserved, we can actually solve for what that final velocity is for that smaller ball. And so since we know, let me write the mass over here. The mass is 1 kilogram. So since we know momentum is conserved, we can say the initial momentum is equal to the final momentum. And so the initial momentum is the initial momentum for both of these balls. And so we're going to have basically mass times velocity. Let's see, plus mass velocity. Let's say this black one is for the black ball. This red is for this big red ball. So all this is the initial momentum. Well, since this black ball isn't moving, the initial momentum for it is going to be 0. So we can basically ignore that part. And so we're just left with this bigger ball, mass times velocity as the initial momentum. And that's going to be equal to the final momentum, which is going to be this scenario over here. And so since this bigger ball has no velocity, we can basically ignore it in the final part and just look at the momentum of the smaller ball. So I'm going to write that in black, mv. So we're trying to solve for this velocity here, that velocity there. Well, we know what this mass and this velocity is. It's basically 5 times 10. And so 5 times 10 is 50. So let me just erase that, make this 50. And we know the mass of the black ball is just 1 kilogram. So let's make that a 1. And so we could solve for the velocity of the smaller ball after they collide. So the mass of the smaller ball, or the velocity of the smaller ball, is going to be, we're dividing 1 over, well, the velocity is going to be 50 meters per second. So notice the bigger ball had only a velocity of 5 meters per second. But once it collided with the smaller ball went a lot faster. Now it's going 50 meters per second. And basically it's going so fast because this ball is a lot smaller, and this bigger red ball is basically a lot more massive. It's bigger. So it transferred all of its momentum over to this smaller ball. And so that's kind of the general idea of an elastic collision. An inelastic collision is when objects stick together, right? So inelastic. So now let's say, basically let's use the same scenario. Try to draw it a little smaller here. Big ball has some velocity that way. Smaller ball. Now let's say they collide and stick together. So now they're stuck together over here. So now that they're stuck together, they're still both moving to the right now. So now they're both moving to the right. So the question is, what velocity are both of these balls moving at now that they're stuck together? So now, using conservation of momentum again, we know the initial momentum is just the momentum of that ball. So the initial momentum is just mass times velocity. So that's going to be equal to, well, now since they're stuck together, but they have the same velocity, both of these masses are going to be added up. So we're going to have basically the mass of the red ball plus the mass of the black ball times phi, right? So all this is final, and all this here is initial. And so using the same numbers, I'm just going to use this velocity initial to be 5 meters per second. Mass of the big one, I think we said it was 10, if I remember right. And let's say, yeah, the mass of the smaller one, that mass was just 1. So now, for this inelastic collision, we again use the conservation of momentum, where this is the initial momentum, this is the final momentum, where the masses are added together because now they're stuck together. So now let's just put in the numbers and see what we get for this final velocity after they collide and stick together. Well, this here is going to be 50. So it's going to be 50 equal to, well, that's going to be the mass 10 plus this mass is just 1. So that's going to be 11. So now solve for that velocity. We divide 50 by 11. And we get the velocity is going to be, well, my calculator for that. 50 divided by 11 is 4.5. I round say 55. Let me say 4.5. So now, after they stick to each other, now the final velocity after they've collided and stuck together is 4.5 meters per second. So notice, after they collide, they basically slow down, or the big ball slows down because it was originally moving at 5 meters per second. But after it collides with the smaller ball, now it's only moving 4.5 meters per second. Okay, so that's the general idea of the conservation of momentum and elastic and inelastic collisions. For the most part, you probably just have to remember that elastic is for when things bounce apart, and inelastic is when two objects stick together. But for both those scenarios, the momentum is going to be conserved. So you can always go back and use your conservation of momentum. Cool. So now let's see, going through the slides here. Boom. Oops, boom. Okay, so next we're going to go over work. We're gonna go over work. And so again, I'm just gonna give you the equation and then try to explain it and talk about it after I give it to you. So work is given by force times distance. Work is given by force times distance. So basically, if I have, let's say I have my eraser here, and I apply a force to it up this way, well, let's say I apply a force over it this way, the amount of work that I apply to this eraser would be the amount of force that I push on it with my hand times this distance here. Basically the distance that I pushed over that eraser. So that would be the work given. So an example would be like if there's some box here, and you push on this box with the force of 10 newtons. Let's say you push it 10 meters. Then the amount of work that you did on this box is going to be, well, the force you applied times the distance you moved it. And so that's going to be, 10 times 10. So the work that you did on this box is going to be 100. And work is measured in joules. This is measured, actually it's units, I should say. Its units are joules. So we usually use a J for that. So you did 100 joules of work on this box. All right, so I think that makes sense. It's not too bad. Well, let's say this box is really heavy and you still applying 50 newtons of force to this box, but it's so heavy the box does not move. Then how much work would you have done on this box? Well, if the box doesn't move, the distance is going to be 0, right? So even though you applied some force, since the box doesn't move, the amount of work that you did is going to be 0. So there has to be some movement. Basically some distance due to the force applied for there to be some kind of work. So if I push downwards on my board here, no matter how hard I push it, if the board doesn't move, the amount of work that I apply is going to be 0. All right. And there's also basically another way we can write out work. We can also write out work as the change in kinetic energy. So we can also write the work as the change in kinetic energy. And I'm kind of jumping ahead a little bit, but I think it's useful to see this here because we're already talking about work. Kinetic energy is a pretty easy concept to, understand. So basically kinetic energy, I use KE for kinetic energy. It's just the energy for something that's in motion. Kinetic means motion. And kinetic energy is given by 1/2 mass times the velocity squared. So this is kinetic energy. So basically if I have a ball here and this ball has some velocity that way, say 5 meters per second, and say the mass is equal to 1 kilogram, I can find the kinetic energy of this ball by just using 1/2 times the mass times the velocity squared, and that would give me the basically kinetic energy of the ball. So the kinetic energy of this ball would be, 5 times 5 is 25, times mass is just 1, divided by 2. So 25 divided by 2, 25 divided by 2 is just 12.5 joules. And so energy is also measured in joules, just how work was also measured in joules. So work and energy are both measured in joules. Cool. And so that's basically kinetic energy. I'm gonna talk a little bit more about that later, but just want to show you here that work can be given by the force times the distance, and it can also be given by the change in kinetic energy. So for example, let's go to the box scenario again. So you apply some force onto this box, right? And the box moves this distance here after you apply that force. So we know multiplying that force with that distance will give you the work. Well, we can also find the work by using a change in kinetic energy. So change in kinetic energy basically means the final kinetic energy minus the initial kinetic energy. So the final kinetic energy minus the initial kinetic energy. That's what that triangle means, right? The change in. And so the initial kinetic energy here initially was basically 0 because the box is not moving yet. So the velocity here is 0 initially. But once you move it this distance d, it now has some velocity over here, some final velocity. Let's say the final velocity is 8 meters per second. Well, if we know initially it was at 0, and after some distance d, the final velocity is 8, then what would be the work done now? Well, if we didn't know the force and we don't know the distance, we could still find what the work is just by knowing the initial and final velocities. So since the initial velocity is 0, this part right here would be 0. Boom. So that's 0. The final kinetic energy is just going to be 8 meters per second. Well, the velocity is going to be 8 meters per second. So here the work is going to be 1/2 mv squared, where the mass, let's say the mass is equal to 2 kilograms for that box. So it's going to be 2 times 8 times 8, and cut it in half. Well, then the work the work, I'm gonna write it right here, the work is gonna be equal to 64 joules. Because the mass is 2 and there's a half there, so the 2's will cancel out, and then the v squared, or the velocity squared, is just going to be 8 times 8, and 8 times 8 is 64. All right, so those are the two ways we can calculate the work. All right, so let's see, going through the slides here. Well, now the slides. Now we're going to talk a little bit about energy. I've already told you about kinetic energy. So another form of energy is potential energy. So we know there's kinetic energy. It's given by 1/2 mv squared. And then there's also potential energy. It's also potential energy. Now, potential energy is basically, you can kind of think of potential energy as stored up energy, right? So I described it a little bit in my last video. If you have something, you know, raised on top of a hill or on top of an incline. So like, if you have a ball up here, and this ball is not moving, since this ball is up here at some height h, it has some potential energy because it can basically roll down this incline and pick up some kinetic energy. So this potential energy is what we call gravitational potential energy because it's up here by some height. And so there's basically different kinds of potential energy. There is gravitational potential energy. There is elastic potential energy, which is kind of like the potential energy in a spring. So let me see if I have anything like that. Well, let me just draw it out. So if you have like a spring, let's say this spring is like pushed in to where I have that box right there. So if I push this box inwards, it's basically going to give this box some potential energy, because once I let it go, the spring is going to push on it and make the box go that way. So similarly, if I were to put this box up here on this hill, and then kind of let it go, and kind of let it go in the incline part, it's gonna then roll downwards. So, but the main form of potential energy that we're gonna be talking about here is gravitational potential energy, and that's given by mass times g times the height, where this h is basically how high up off the ground that object is. So the higher off the ground, or the higher the h is, the higher potential energy something has. All right, so now let me talk a little bit about the conservation of energy. Conservation, hope I spelled that right, of energy. So just like how we have a conservation of momentum, we also have something called the conservation of energy, which basically just means the initial energy the initial energy is going to be equal to the final energy. Now, this is only true if there is no energy loss or basically no energy loss in the system. And so an example of conservation with energy would be like, let's say I'm standing up here and I have a ball in my hands. So I'm standing up here at some height, h. Now let's say h is 50 meters. So you're pretty high up there. So you're standing up here at some height, 50 meters up. If you drop this ball from the top, what would the velocity be once the ball reaches or falls 50 meters? Well, here we could say energy is conserved because no energy is being lost to the system here in this situation. So we can use conservation of energy where the initial energy would equal the final energy. Well, if we drop the ball from rest because we're initially holding it, the initial kinetic energy is going to be 0. And so let me rewrite our conservation of energy here. Write it like this. So potential energy initial plus kinetic energy initial is going to be equal to potential energy final plus kinetic energy final. Well, initially, when it's up here, the kinetic energy is 0 because the ball is not moving. So we can ignore that part. But since it is up by some height, it does have some potential energy. And so it's going to be mgh, which is the potential energy. But then once this ball gets to the ground, the potential energy is going to be 0 because now it's on the ground level. But it is going to have some kinetic energy. So we can ignore potential energy final and just look at the kinetic energy. Once it gets to the bottom, that's going to be 1/2 mv squared. So now we're trying to find basically this velocity once it gets to the bottom, right? So this velocity we can solve for because we know basically g is the acceleration due to gravity. And we can cancel out the mass on both sides because the mass is going to be the same, right, initially and finally. And so this v here is going to be given by, well, let's see, multiplying 2 over, we have 2gh. And then we also have to take the square root of v, right, because it's squared. Boom. So the velocity at the bottom is going to be 2gh. And so we can actually solve what that velocity is because we know the height is 50. And so that's going to be equal to the square root of, well, 2 times 10 is 20. And so there's 20 times 50, that's going to be 1,000. The square root of 1,000 is square root of 1,000.000 is 31.6. Boom. Meters per second. Boom. So this is a kind of useful thing here, the conservation of energy, because just by only knowing how high up we are, we can find the velocity of something if we drop it up there once it reaches the bottom. And it's going to be 31.6 meters per second. All right. So that's the general idea of the conservation of energy. So next, let's see, going through the slides here. It's like next they talk about power. So I'm just going to talk about power a little bit, just so that you've kind of heard it before. Power given by P, a capital P though, whereas momentum was more like a lowercase p. Power, which is a capital P, is given by the work divided by the time. So basically power is how fast work is, how fast work is done. So basically the faster something is done, or the faster you do your work, the more power you have. And power is measured in watts. And so let's go back to the box scenario here. Right? And so let's say, you push this box a distance of 10 meters and you apply a force of 10 newtons. And so the work here, we know is just force times distance. So the work is going to be, 100 joules? Now let's say you push that box 10 meters in 5 seconds. So let's say the time it takes is 5 seconds for you to move it from there to there. Where the power required for you to move this box 10 meters in 5 seconds, if you push it at 10 newtons, the power required is going to be 100 divided by 5, right? So that's going to be, what is that, 20? It's going to be 20 watts. Boom. So let's say somebody asks you to push this box 10 meters in 1 second instead of 5 seconds. They want you to move from there to there in 1 second. Applying that same force, well, the power required to push this box this distance in 1 second, would be 100, because that's the work, right? So 100 divided by 1, which is the time. So the power required is going to be 100 watts. Boom. So a lot more power is required to do things at a faster rate, right? Because power is basically how fast work is done. So the faster you do something, the more power required to do that task. All right, so just looking through the slides here, looks like now they're talking about potential energy. I already went over that a little bit. Now they're talking about the work energy theorem, which I also discussed that. Well, let's go over this problem here on slide number 58. I think it's a good one. So slide number 58 says, consider a problem that asks for the distance a fast-moving crate slides across a factory floor in coming to a stop. The most useful equation to the problem is, well, they gave you some options here. It's A, F equals ma, B, Ft equals the change in momentum, and C, kinetic energy equals 1/2 mv squared, and D, Fd equals the change in kinetic energy. So we're basically trying to find, it says find basically the distance. Find distance. And we usually represent distance with the D, right? So that's what we're trying to find. Well, off top, you can just kind of look at these equations and we see basically this first one is just Newton's second law. And so this gives us no information about any type of distance. The second one is the impulse or the impact equation. And I wrote it as the change in momentum. On the slides, they write it as the change in mass times velocity. But, same thing, right? So this tells us nothing about the distance either. So, no, it's not that one, not that one. Well, this one just gives us the kinetic energy. It tells us nothing about distance. But this last one, is what we call the work energy theorem. And so, force times distance is basically the work, right? So this is basically saying work equals the change in kinetic energy. And this is that equation that I went over a little bit a little while ago. And so we see here, work is force by distance. See, there's the distance D that we're trying to find. So we can just automatically choose this one, because this is the only equation that even has distance involved in it. All right, so again, this one is Newton's second law. This one is the impact equation. This is just kinetic energy. And this is the work energy theorem. All right, so now the last thing I'm going to briefly talk about is going to be machines and efficiency. So machines and efficiency. How do you spell that? I-C-I-E-N-C-Y. I think that's how you spell it. So machines and efficiency. Well, a machine, if you're looking at the slides, I'm not sure if it says it in the slides. Well, a machine is basically a device. It's basically a device for multiplying or changing the direction of a force. And so a machine is basically a device for multiplying or changing the direction of a force. So just to kind of give you an example of like a very, very simple or basic machine would be like a pulley or a lever. So this right here would be like a pulley. So if you pull on basically this pulley, so if you pull downwards on this pulley, this block is going to go upwards, right? So basically this pulley is a type of machine because it's changing the direction of a force or the force that you apply. So similarly, a pulley is a kind of machine. Another kind of a simple machine is a lever. So if you have so say we've got a box right here and you're on this side, right? If you push downwards on this lever here, it's basically gonna make this box go upwards, right? So this lever here is a machine because again, it changes the direction of the force. Okay, and so for every machine, the work in is going to be equal to the work out. So for like those two examples I gave for the pulley and the lever, the amount of work that you put into either that pulley or that lever, the amount of work that you put in, or I can write it this way, the amount of force by the distance that you put in is going to be equal to the amount of force times distance that's going to come out. So the amount of force that comes out does not have to be the same amount of force that you put in, right? I mean, that's kind of the whole point of a machine. Because let's say you want to put in a little bit of force. We put in a little bit of force, but then basically a lot of force can come out, depending on the machine. So I think there's an example here on the slides. So if you look at slide number 71, it says, in an ideal pulley system, a woman lifts a 100 Newton crate by pulling downwards on a rope with a force of 25 Newtons. So we have some woman here, and she basically lifts this crate upwards by pulling downwards on it, right? So she's pulling downwards with a force of 25 Newtons. But we know this box weighs, the weight of the box is 100 Newtons. So then it asks, for every 1 meter that she pulls downwards, how much will the crate rise up? Well, since this is a machine, right? We could say the work in equals the work out. So that's going to be basically the force times the distance in equal to the force times the distance out, right? Out. So over here, this is the side where she's putting in the work. Over here is, where the work is kind of coming out. So she puts in 25 Newtons and she pulls the rope down 1 meter. So let me write it right here. So she puts in 25 Newtons times 1, because she pulls the rope down 1 meter, and the force she puts in is 25. It's going to be equal to, well, the box weighs 100 Newtons. So that's going to be 100. And D, this distance D, is going to be how high this box is lifted upwards. So we can solve for this D here by just dividing 100 over, right? So that's going to be 25 divided by 100 equal to D. Well, it's going to be basically 0.25 meters. So for every 1 meter that she pulls on this rope, this box is going to be lifted up by 0.25 meters. Or I can also even write this as, that's basically the same as 25 centimeters, right? So that may not seem like that's that high, but notice how she only pulled down with a force of 25 newtons when this box weighed 100 newtons. So normally, to pick up a 100 Newton box, you would have to put in at least, right, 100 newtons of force. But because of this pulley system, she can lift the same box, but she only had to put in a force of 25 newtons, and it was able to be lifted. So she can basically just continue to pull on this rope, and it'll go as high as she needs. And she only has to pull on it with a force of 25, even though this box weighs 100 newtons. So that's basically the whole idea of a machine. A machine is supposed to make, work easier. So you can lift heavy things, even though you can only lift with only so much force. All right, so lastly, I'm just going to talk about efficiency, where efficiency is just how well a machine works. So basically, the more efficient a machine is, the better it works. It basically means all your energy is transferred over. And so let me just give you the equation. The efficiency, let's just use EFF, is equal to the work done divided by the energy used times 100%. Okay, so I'm just going to give you the equation for that. I don't think you'll get so many questions on efficiency, but if you do, it's basically the amount of work that you did, or the amount of work that was done, divided by the amount of energy that was used, times 100%. And so basically, the higher your efficiency, the higher the efficiency. That basically means less energy loss. And then the less the efficiency, that means the more the energy loss. All right. So that's about it for this chapter. I don't think this chapter is too hard, maybe a little bit tricky, just kind of keeping up with all the equations, but just go through it, do the best that you can. Again, this is a summer class, and this is a lot of information that we're trying to put into you within a short amount of time. Basically thousands and thousands of years of information that you're learning within a month, So don't stress out too bad if you don't understand it all. Just do the best that you can and keep it up.